Although agriculture has been a driving force in civilization, making great technological strides, these advances have never been a safeguard against collapse. Food systems have swayed between times of prosperity, boom, and hardship, bust. The most famous scholar to articulate the tension between food abundance and overpopulation was the Reverend Thomas Robert Malthus. In his book, An Essay on the Principle of Population, Malthus argued that an increase in food production improved the well-being of the populace, but that the ensuing population growth would eventually negate any benefit. His theory has become known as the Malthusian trap or the Malthusian specter because of its gloomy conclusions. From a mathematical perspective, Malthus argued that population increases exponentially while food production increases at a linear trajectory or straight line. As shown in the chart, the power of geometric progression eventually outstrips food production at the point of crisis. Of course, this happens without thinking about the challenges that food production face, including soil loss, climate change, agricultural pests and diseases, economic fluctuations, and civil unrest. To review the boom and bust cycle over time, let's start by looking at the technologies and innovations that spurred the growth of agriculture. Major advances like irrigation around 6000 BCE and the plow around 3000 BCE brought enormous gains in productivity that helped to spur growth in populations. In many cases, however, these same innovations contributed to long-term losses in soil fertility. This is when nutrients and organic matter are removed from the soil and not replaced. Some of the major culprits for this are overcropping, stubble removal, salination from irrigation, soil erosion, and frequent tillage. This has caused some pundits to exclaim that in the history of civilization, the plowshare has been far more destructive than the sword. Speaking of swords, let's mention Rome. By the beginning of the Common Era, the farmland surrounding Rome had been so depleted that Romans relied on wheat shipments from over 1,000 miles away from Egypt and North Africa. Commenting on how a reliance on distant food sources can leave a region vulnerable, the Roman Emperor Tiberius wrote, "The very existence of the people of Rome is daily at the mercy of uncertain waves and storms." After the fall of the Roman Empire, a favorable climate aided the growth of European agriculture. By 1300, Europe's population reached 80 million, and the global population reached 360 million. But the limit of what food supply could support had been reached. Over the following centuries, poor weather, shifts in climate, and degraded soil dampened agricultural production. Meanwhile, parts of Europe periodically fell into famine as its food supply struggled to keep pace with the growing population. By the 17th century, European farmers had managed to increase crop yields by promoting the use of crop rotation, cover crops, and the use of animal manure to fertilize soil, as well as other practices that I'm not mentioning. But as before, even with these improvements to agriculture, population growth overtook the increased food supply, leaving large segments of the population in a state of malnutrition. For example, the Russian famine from 1602 to 1603 was proportionally one of the worst for that country, killing perhaps 2 million people, a third of the Russian population at that time. And yet the population continues to grow. Between 1650 and 1850, the population more than doubled from roughly 550 million to 1.2 billion. By 1900, it had reached 1.6 billion. So what was it that allowed this population to increase? This growth was supported by the so-called global agricultural evolution. As part of the Great Columbian Exchange, new crop varieties from the Americas, such as corn, sweet potatoes, and cassava, rapidly spread across the globe. In the 1800s, a favorable climate and fertile soil turns the U.S. into an agricultural powerhouse that provides grain and then meat to Europe. And then also in the 1800s, improved transportation from railroads, packaging, food processing, and refrigeration helped to distribute this food. Due to the boost in agricultural production in the 1800s, by the beginning of the 20th century, farmers faced a new crisis, dwindling supplies of nitrogen-based fertilizers. It just so happened that air is 70% composed of nitrogen, but no one knew how to capture it until the German chemist Fritz Haber tested an effective process in 1908. After Fritz teamed up with Carl Bosch, the Haber-Bosch process was scaled up to produce commercial quantities of ammonia by 1910. By 1918, Fritz had won the Nobel Prize in Chemistry, and the Haber-Bosch process went on to feed the majority of the world. It wasn't long before a new collection of technological advances created the Green Revolution, which really has increased food production more than anyone ever expected. Starting in the 1930s and running through the 1960s, the Green Revolution consisted of 4 components. The first component is synthetic fertilizers, and as we discussed, this was launched by Fritz Haber. They consist mainly of inorganic compounds that are petroleum-based. As the pictures in this slide show, fertilizers are very effective in promoting growth, here with tomato plants and especially in nutrient-poor soil. One important distinction between organic fertilizers and synthetic fertilizers is that synthetic fertilizers feed the plant directly, while organic fertilizers feed the soil, which then create the organic matter and the micronutrients and organisms that then feed the plants. The second component of the Green Revolution is chemical pesticides. Billions of kilograms of pesticides are applied each year, and the price tag is billions of dollars. What's interesting is even after these pesticides are applied appropriately, 37% of all crops are still destroyed by either insects, that's destroyed by 13%, by plant pathogens, which destroy 12%, and weeds, which destroy another 12%. And it's estimated that less than 0.1% of the pesticides applied to crops actually reach their target pests. The third component of the Green Revolution is high-yielding varieties of staple crops, such as dwarf wheat. These plants were high-yield, they were disease-resistant, they had strong, sturdy stalks that were short and could hold lots of seed heads. They grew very fast when given fertilizers and irrigated. In fact, they were so successful that agricultural production outpaced population in Mexico, India, and Pakistan in the 1960s and 70s. The picture here shows Norm Borlaug, who's considered the father of the Green Revolution. This is because of his work developing high-yielding varieties of dwarf wheat. The fourth component of the Green Revolution is mechanization. In this slide here, we see an ad for a tractor company that is saying that its tractor drives like a horse, does the work of 10, but eats only when at work. Not only are tractors more powerful than horses, but because you don't have to feed them, you can devote more of your property to cash crops. Mechanization also proved to be very efficient, either because it completed tasks very efficiently and quickly, or it combined tasks. So for example, in the combine harvester, 3 tasks were completed: reaping, or cutting down the plant; threshing, which removed the seed from the plant; and winnowing, which removed the seed covering from the seed itself. This was all done with one machine. So, as we've seen through history, this amazing increase in agricultural production has led to a boom in population. And even though the population growth rate is going down, the overall population is still expected to rise. And in this chart, it has the global population at 11.2 billion by the year 2100. So as we look ahead, we can ask, was Malthus right, or will human ingenuity avoid another calamity? I want to thank the Center for a Livable Future at Johns Hopkins University for providing information to make this lecture possible.